All right. Hello, everyone. I hope your week is going well. Just a reminder of where we are at schedule-wise. You just submitted homework 4 the other day. Homework 5 is available to you, so hopefully you've got started on that. It's due on the very last day of class. Just as a suggestion to you all, please get a start on that before break if you have the time to do so. I know it's a busy time of semester. I know you may not have the time to do so, but if you do have the time to get started on that before break, future you will appreciate it. So please take some time to look that over, get started on it, ask questions. I've got office hours tomorrow. Love to chat with you about that homework assignment if you want. Homework 3 is graded, and you should have your grade back now. Should be in your repository, should be on Canvas, so please take a look at those. If you have any questions, if you don't understand why something came out the way that it did, you can email me, you can hit me up on Piazza, you can come see me in office hours tomorrow, and I will be happy to go through the assignment with you if you want. Or we can set up an appointment for next week. If you want, just let me know. Let me know what you want, let me know what you need, and we will make it happen. So obviously with Thanksgiving break next week, we're only meeting on Monday. We won't be meeting on Wednesday. So we've got next Monday, we've got the Monday after that, and then we've got an exam review session, and then the final exam. So we're getting very close to the end here. Does anybody have any questions in terms of homework assignments or other scheduling stuff before we hop into today's topic? Yes. I will be in my office hours on Tuesday next week. Yeah, next Thursday is Thanksgiving, so I won't be here that day. But Tuesday is actually a fairly open day for me. So if you are still on campus on Tuesday and you want to make an appointment with me or come in and have a chat with me, Tuesday is a fantastic day to do it. Shoot me an email and we'll get something on the calendar. Monday is not quite as flexible as Tuesday, but yeah, let me know what you want. Let me know what you need. We'll set it up. Anything else we could chat about before we hop into today's material? All right, so we're going to keep talking about NoSQL databases, but we're going to talk about some different kinds of NoSQL databases today. So all the NoSQL stuff that we've been talking about up until this point has really kind of been focused around document stores, and there's good reason for that. Document stores, databases like Mongo are extremely popular and becoming more popular. So I think it's important for us to have conversations about document stores. I think it's useful for us to spend a little bit more time talking about those. But they are not the only type of NoSQL database that exists in the world. So what I want to do today is kind of give you a tour of 2 more types of NoSQL databases, key value stores and graph databases. We're going to take a look at some examples of both of those. Before we get into that, though, I do think it's worth mentioning that there are other types of NoSQL databases that are out in the world that we are not going to get time to talk about. Maybe the biggest category that we haven't talked about yet and won't talk about are column store databases. So it's another category of NoSQL databases that you may want to look into. Probably the best known column store database is Cassandra database, which is owned and managed by Apache, who makes the web server software and a whole bunch of other stuff. Be another category to look into if this kind of stuff interests you, if you're trying to make database decisions. But we're going to take a look at key value stores and graph databases. Not only are they very different from document stores, Mongo, that we've talked about before, but they're also very different from each other. These are 2 very, very different types of databases that we're going to be talking about today. And that kind of has an effect on their usage, what their utility is, what they're commonly used for. So let's start by talking about key value pairs. The example key value pair key value store that we're looking at is Redis. That's the specific implementation. Again, it's not the only key value store that exists, but it's by far the most popular. Many of the large players are using Redis. So Amazon, definitely. Actually, the name Redis comes from a website you may have heard of called Reddit. Reddit's using this technology. Amazon's using it. I believe Facebook's using it. So it's definitely very commonly used, very popular type of database. And actually, the word database can be a little bit hard to decipher when it comes to Redis, because you'll see that it's described here as an in-memory database, which seems a little bit confusing. It only lives in memory. So think about what that means. My database is entirely in memory. What happens when I turn the computer off, or the computer crashes, or something happens, right? Bye-bye. All the data is gone. All the data is now not in my database anymore. So actually, another word that you might hear, thrown around with Redis is it's actually used for caching. It's a cache. It's an in-memory data cache. And so a lot of what we're going to be talking about, a lot of the examples that we see that use Redis are using information that is temporary, that is not super critical to keep around forever. Or if it is super critical to keep around forever, we're going to make another copy of it in a more permanent database, like a SQL database or a Mongo database, right? Redis is almost never going to be used exclusively by itself. There's almost always going to be a backing database. There's almost always going to be another MongoDB or a SQL database behind Redis that takes care of the permanence, that takes care of the persistence side of things. And Redis is going to sit in the middle and act as a cache. Why? Why would we bother doing this? What's the big gain that we get out of that? It's a word that starts with a P. Rhymes with, I don't know what it rhymes with. It's, yeah. Take stress off the server. It's all about performance, right? If I can avoid taking trips to database, that's going to save me time. Trips to disk are slow. They're slow. So let's store a bunch of stuff in memory if we can. And some of the trajectory of computing has made this possible. Memory is cheap. Memory is very cheap these days. It's not very expensive to upgrade how much memory you've got. So very doable for me to keep some of this stuff in memory and avoid trips to disk, avoid trips to the actual database if possible. That's the whole purpose of a cache. So it's very much trying to mimic the cache that you might have learned about in your computer architecture class, but at a database level, in the memory level. It's the same general concept. That being said, there are ways that we can enforce persistence using these key value stores. We'll talk about that a little bit later. So, when I say key value store, I mean it quite literally. I have a piece of data. The key is hello. The value is world. Doesn't really get much more complicated. Well, it does get a little more complicated than that. We'll see in a little bit. There are data types involved that we'll talk about as well. This looks like a very short list of data types. And you might be thinking to yourself, okay, he's just giving us the highlights. And that's true, this is the highlights, but it's also the entire list of data types that exist for this database. There are no additional data types that Redis provides outside of these. Now, some of these are fairly straightforward. Strings, lists, sets. We've seen those things before. Hashes, you can probably imagine what hash is. But wait a second. We're talking about a key that refers to a value where the value is a hash. So it's sort of a double layered affair, right? One of the real magical data types, though, and one that we're going to spend a chunk of time talking about, is this last one, this idea of a z-set. A z-set is like a set, but it's an ordered set. We'll talk about why having ordered sets is a potentially useful application in just a little bit. So what I want to do for you is just give you some brief introductions to how we can interact with some of these data types, how a Redis database actually works. I've got it on my computer. You can go out and download it and install it if you want to, although a little word of caution, Redis really wants to be on a Unix-based system. You can run it on Windows. I'm about to do so, but it's, just be prepared. You might have to do a little bit of jumping through hoops to make that work. So it's a client-server architecture. Really, is this too big? Oh, man. Okay. Whatever. So I need to start the server first. And I cut the server off. Yeah, it is just redis.server. All right. Just making sure. So we'll start the server first. There we go. And remember, this is an in-memory database. So I just started. What's in there? Nothing. Nothing. Because the last time I shut it off, anything that was in there is now gone. It does not have persistence. It's going to keep printing out these annoying system messages every couple seconds, isn't it? Oops, that's not what I wanted. I was going to start the client, but I don't want to start the client on this tab. Let me open a new command line. Sorry. This will just take a second. Redis in. No? Oh, it's 64-bit. Sorry. All right. And now we will start the client, which should hopefully connect to that server that's running in the background. And we get a prompt, much like we saw with Mongo yesterday. And now I can start spelling out the operations that I want. One thing that I think is really important to notice about the operations that I'm about to show to you. So you can see very simple operations here. Set hello world means, set the key of hello to have a value of world, right? Seems very straightforward, and it is. But I want you to be aware of the fact that try and think of a SQL command or maybe even a Mongo command that is similar to the action that I just performed here, right? SQL commands especially take sort of a roundabout approach to finding data and manipulating data. It's like, all right, start with the big giant data set, narrow the data set down to what you need, right? Apply constraints to the data set until you find the specific set of data that you care about, right? That's what a query is. And then if I want to change some of that data, I can change some data. Here, I'm just specifying an option directly. Take this piece of data associated with the key. So I'm issuing a much more direct data manipulation command. I don't have to specify anything about filtering out stuff through a data set. There's not really a way to filter in Redis. That's not a piece of functionality that's necessarily built in. I'm performing operations. I'm performing data operations. The way that I access and manipulate data is just a series of operations. So I can, access any keys that I've set before, and it will dutifully return the value. I can delete the keys, and it will give me a 1, which indicates that it was successful. The deletion, the deletion worked. And if I try to retrieve a key that doesn't exist, I get a good old null value back, right? So strings aren't particularly interesting, but let's take a look at some of the more interesting data types that Redis provides to us. And it's a similar story. I'm not talking about tables with rows and columns. I don't have a way of fetching rows, columns, things like that, because they don't exist. I am manipulating data directly via a set of commands. This database is a much more direct, a much more operational interaction with my database. So you can see here that in order to insert data into a list, I'm using an rpush command, where push sounds very familiar to us, right? Rpush list 1, what did it say, hello? So can you decipher what rpush is probably telling us to do? Push on the right side. There's an lpush command that would tell me to push on the left side. So depending on what I need, I can treat a list as a stack or as a queue by using the push and pop commands on the appropriate sides, right? So They're trying to make this as flexible as possible to keep the number of data types low. I want to keep the number of data types low. We're trying to get rid of as much overhead as possible, get rid of all the crap that you know, SQL and other databases have included that, quite frankly, are not strictly required in every situation, all for the sake of performance, all for the sake of trying to make this go as fast as possible. So I can add stuff to, whoops, I didn't mean to open Chrome. Why did I do that? I can add stuff to my lists. So if we want to add some more list items. Oh, and now see, it's returning the length of the list that I'm manipulating. It's telling me how many items are in my list. And then I can use commands like range to give me what items are in my list. So all of the items from 0 to -1, that feels like a Python kind of statement, right? For those of you who are familiar with Python, feels kind of like a Python-y kind of statement. So was it LRange? LRange, sorry. LRange, list 1, from 0 to -1 will give me all of the contents, and I can change the indices to whatever I want them to be, right? Sorry. I made the text a little too big, I guess. It's still too big. Okay. So I can slice my list however I need to find the values that I'm looking for, right? This is all pretty straightforward stuff. There's the pop command to remove stuff. Let's take a look at sets. So a set in the traditional sense, right? I can add items to sets, and then I can test for membership. Remember, sets are not ordered, so iterating through a set is not really actually iteration looping is not really something that Redis wants to consider. So I can sadd, that's right, set1, and then give it to, really? It's still going off the bottom of the screen? What did I do wrong with this window? I'm sorry. I'm trying to make this stuff fit. It'd still be big enough for you all to read it. I'm doing a terrible job. So we can add stuff to my set, and then we can check to see if certain things are members or not. Whoops, I forgot the key. My fault. So item 2 is a member, but item 5 is not, right? Because I never added item 5, right? What is the advantage? So I know I've mentioned this multiple times, right? What is the advantage of keeping these commands so simple and avoiding a lot of the? I mean, what are we gaining? How is the performance achievement gained by keeping these commands simple? What is it that a SQL database is doing, a relational database is doing, when it processes commands that we no longer have to worry about by using data manipulation commands directly? We spent time talking about it in class. I write a SQL command and I say, run this query. Before it actually executes the query, what's it got to do? Yeah, we got to parse it. We got to turn it into a tree, right? And then we got to take that tree and then we got to optimize it, right? And then once the tree is optimized, all right, then we'll execute the query. So that's a lot of steps in between. Here, we don't have those steps. The command is what is happening, period. How do I optimize this? How do I make this command any faster than what it is? You can't. That's what it is. That's part of where Redis gets its performance speed up. We are taking things, breaking them down into absolutely small bite-sized chunks to avoid a lot of the overhead, avoid a lot of the extra processing that the relational database servers are performing for us when we submit a query. So other things you can do with sets that aren't on this list, you know, the traditional set operations like intersection and union and all that stuff are also fair game here. I really want to get to the Z sets though, so I know I'm going a little quickly through here, but here's some hashes. Hashes get a little confusing because I have a key that's associated to a hash table. So there's actually two keys here. I've got the key for the table itself and then another key into the table, right? This key tells me what hash table I'm referring to. This key tells me what key I want within this hash table. So I've got two keys to one value. It's just an additional layer that I can use to organize my data. But let's skip through that and talk about Z-sets. This is what I've been really wanting to talk to you about. This idea of a Z-set. So it shares this concept of a set with the concept of having some order associated with it. So you'll notice that when I add stuff to a Z-set, I'm adding a label. You can think of member one as a label, right? For a numeric piece of data. In this case, what does the 728 represent? I don't know. 982, I don't know. That's the score I got on my math SAT, right? Not really. It's not even possible. But so we have two pieces of data. We've got so first we have the name of the key, Z-set. That's the name of the Z-set, followed by some numeric value, followed by a label for that particular piece of data. And we can add some other stuff here too. 984, member 0, right? So I've got two things in here now, member 0 and member 1. And when I insert things into this Z-set, it's actually going to keep them in sorted order by whatever this numeric value is. Whatever that numeric value is. That's where the Z comes in. It's short for probably like Z-score, where I'm keeping track of, well, maybe not actually. Anyway, and so then I can grab the values back in that sorted order automatically. So when I ask for a range of values, if I ask for like this set here, Z range, Z set, from 0 to -1, and I say with scores, you can see that it's going to give them back to me in sorted order. Member 1 has a lower score, member 0 has the higher score. If I insert another one in between, 803, member 4, and then I ask it to pull back out, you'll notice that it's stuck it in the middle, right? It's returning the values of the set in sorted order. And I know I'm making a big deal out of this, and I know that I'm saying this is one of the nice things that Reddit provides to you, and I want to provide an example of why these Z-sets are so useful, why I've been talking about them so darn much. But before we get to that use case example, let's wrap up a few loose ends. Earlier I mentioned that there are ways that we can have persistence with Redis. So one thing we can do is I can take a periodic snapshot of memory and save it to disk, which is actually not a terrible thing to do when you consider that, you know, how much memory is a computer going to have. Even if it's got a bunch of memory, that's still what, you know, still in the gigabytes range. So it's not a huge chunk of data that we're talking about. So I can take a periodic snapshot and store that to disk, and there are still log files that are usually not included by default. I have to go out of my way to tell Redis that I want it to use these log files, but if that's something that I want, it acts very similarly to a transactional log file where every operation I perform gets appended to the log file, and if I want to recreate my Redis database, I can just go through the log file and reapply all of the operations that have taken place. So these options are available, but like I said, for some of them you have to go out of your way. Redis really doesn't want to have to deal with this stuff. It would much prefer that you didn't use this stuff, that you use some other database, some other relational database or other persistent database on the back end to handle those needs. And then what should we use this for? So we talked about the data is going to be temporary, perhaps. We talked about the data as being maybe not mission critical, perhaps. So think about use cases where those things are true. Session information. Sessions are by their very nature temporary. The amount of time that I am interacting with a website is temporary, right? Or even if I never, I never disconnect the session will eventually time out regardless, right? The session's not going to live forever. One way or another, somebody's going to put an end to it. So any information that I need to record about the session, any encryption keys that might be used or other things like of that nature, or actually I don't know if Redis is secure, yeah, maybe. But any other information that's just related to a particular session could be stored in Redis, and we have quick and easy access to it. User profiles. So the reason why this is here is anytime you go to a new website, they ask you to create an account. A lot of times they're going to want you to create a user profile. Keep in mind that it takes time for me to fill that information out, and oftentimes, depending on the website, there might be multiple screens, that I'm going through, and so I can use Redis to kind of remember each step along the way the information that's been edited, so that if I need to go back and change something later on, it can quickly and easily pull that up. And I don't want to store the complete user profile information until I have all of it. So inserting a partial user record into a permanent database, like a SQL database, would be inappropriate. Having those null fields, not being able to properly specify those relations would not be appropriate. So I can store this temporarily incomplete user profile in a cache. And then when I am satisfied that the record's ready to go, I can make that persistent. Another classic use case, Amazon uses it for this purpose, shopping cart data. So if I'm browsing Amazon at 3 in the morning and I put a whole bunch of stuff in there, let's say you fill up your shopping cart with stuff that you want to buy. You don't actually buy it yet though, right? You just put some stuff in there, you want to keep track of it, and you're like, I'm gonna do the smart thing. I'm gonna go to sleep and wait for this buzz to go away, and then I'll see if I want to buy this stuff in the morning, which is how it always happens, right? So let's say you wake up the next morning, you go onto Amazon, and for some reason all that shopping cart stuff was gone. How upset would you be? Maybe a little bit. Part of you might be relieved, right? Like, oh, whew, I'm glad that didn't happen, right? The point I'm trying to make here is that the worst case scenario if I lose shopping cart data is what? I have to go back and find all those items again and put them in my cart again. Like, is it inconvenient? Yeah. But guess what? Amazon wants you to go look at all that stuff, because then maybe you'll buy some other stuff too, right? From Amazon's perspective, that's a good thing that just happened. Now you're going to look at more shopping pages. Now you're going to buy more stuff. So having this shopping cart data being stored permanently is not necessarily a big deal. Losing that information, not necessarily a big deal. Or we can store that in a cache temporarily. We don't need to take up our precious database space and time with that data. So these are some examples of use cases. Let's take a look at another popular use case. This is a website that you might recognize because it says on the top there, but if it didn't, you would probably be a little surprised because this is a blast from the past. This is a very primitive version of Stack Overflow. I feel like it's getting worse and worse for me to say that I remember a world where Stack Overflow didn't exist. That's kind of makes me feel super old, but it's true. I remember looking at versions of Stack Overflow that looked similar to this, right? Anyway, the point I'm trying to make here is that this is one of many websites where users make posts and then other users vote on those posts, right? Reddit, another classic example, certainly not the only ones. So I can give a thumbs up to indicate that I liked something. And then the idea here is that the posts that people like the most, the posts that people care about the most, are going to rise to the top. and the posts that people don't like so much are going to sink. And so we'll only be able to see the good stuff, and the bad stuff will be naturally filtered out. Well, let's ask ourselves some questions about this, right? Do I need to store every single vote in the database? Is that something that I need to keep a permanent record of? The answer to that question might be yes, and actually I could buy that argument, right? But do I need to, if I lose some votes for some reason, how big of a deal is that, right? Let's say I click like on a post. For whatever reason, I come back tomorrow and it just forgot. Maybe that's happened to you, right? I feel like it's happened to me before on some of these sites. Oh, I swear I clicked the like button there, come back the next day, and it never registered, right? What's the big deal? I just click like again, right? I click the upvote button again. Nobody's that upset. Not a huge deal to lose some of that data. The real thing that I care about here, though, in terms of actual data storage, is more along the lines of, let's say a post gets really popular. It's going to get thousands of votes, right? Do I need to store all of the vote tallies that it gets everywhere along the way? Not really. The only thing that I really care about is when that vote tally kind of stabilizes a bit and people stop voting on it, or maybe the voting window is closed. What's that final tally? That's what I really care about. And I also maybe care about like not letting people vote multiple times on the same thing. So restricting how many times I can vote. Those are the kinds of things that we really care about. So, how can I use Redis to maybe handle the temporary situations that are in between, and then only store the data in the proper database when that first period of fluctuation is kind of settled out a little bit, right? Kind of calmed down. So we're going to take a look at an example use case for a site similar to Stack Overflow or Reddit that can track people's voting behaviors on these kinds of websites. So the first thing we'll take a look at is an example of how we might refer to an article in such a system. Here I can see that I've got a key where it's just the word article followed by some unique identifier. And it's a hash table. Every article is going to have the same general structure: title, link, who posted it, what time they posted it, and how many votes it's got. Right? I want every single article to follow this same format. Is Redis going to enforce that format for me? Make sure that every single article has a title and a link and a poster and all that stuff? Is Redis going to make sure that those fields all exist and are properly formatted? Heck no. What's that an example of? It's done on the application side, right? So we call that, what is it? I hear whispers, but I can't quite make out. We talked about this. Mongo did the same thing. So in a relational database, there would be something that would verify a format for us, right? You have to have this many columns. The columns have to follow these data types. What's that called? A schema. So this is an example of an implied schema. It's an example of an implied schema. Yep. So this is what an article might look like in our Redis cache, in our Redis database. Here are some Z-sets that can track a couple of very important pieces of information for us. We've got one Z-set that's ordered by time. These are timestamps. That's going to help us because a lot of times we don't want to show articles after they're a certain age, right? If articles are really old, I don't necessarily want to show those anymore. Or maybe I want to filter by age, right? So having a Z-set lets us naturally sort articles by time. So if I'm showing you only the newest stuff, I just grab the top 10 articles out of this Z-set. It's automatically ordered by time. Or maybe I want to do it by score, by And by score here, what do I really mean? It's not just votes, but it's a combination. It's votes and time, right? It's votes and time. So time matters, but also the number of votes matters. So that's why you see these very large numbers here. It's because it's the time plus however many votes there are. And again, if I'm doing something like this, that implies that, okay, a post with a really big score from yesterday is maybe still more relevant to me than a post with a lower score from today, right? It gives us another way of filtering and displaying these results. So if I want to display the top results from the last day or so, I can just grab the top chunk, the top X posts from this Z set, and show them to the user. So here's where the real magic happens. We're going to start taking these Z sets and building some other structures that we can use to kind of help us organize user preferences. For example, who's voted on what? Very clearly, that's going to be some kind of a set where this number refers to the number of an article, like we saw in the prior data structure. So who all has voted on the article with this number? That's just a simple set of users and their user IDs. If I wanted to, then I could, for example, find preferences of users by taking intersections of these and finding groups of articles that were voted on by the same people, right? That could help me decide what kinds of things to target to a particular person. Okay, you like these articles. Let me find some other similar articles to that to target to you. Or we can take this even further. If we take a look at, I'm sorry, this is actually just showing the two sets in practice. So the Z set and the set. If somebody clicks on the vote button, we increase the score, which brings it higher up on the list, and we add the user into the voted set. So just kind of a rehash of the past two. But then I think where Z sets are really, really nice to see is that I can have a set that does some groupings and a Z set that does ordering by scores. And then I can use set operations. I can combine sets with Z sets to generate useful groupings for me. So for example, if I have a group of articles that I know are related to a single topic, like programming, I have another Z set with the scores of all of the articles that exist and their scores, their rankings. If I take the intersections of those two, the set and the Z set, what do I get? I get a Z set that has all of the programming articles ranked by score. So a very simple set operation allows me to quickly group and organize my data without having to do things like group bys or aggregates or anything of that nature. There's no way to do an aggregate in Redis. Redis doesn't have that functionality. You have to get very clever with your usage of sets and be comfortable doing set manipulations like intersections, unions, and things of that nature. And this is exactly how sites like Reddit do it. When I click on programming subreddit, right? It's going to have a group of programming articles. It's going to grab, the intersection of those articles with the articles ranked by score, and that's what I'm going to see on the programming page. That's maybe a watered down version of what happens, but it's at a very high level exactly what happens when I go to those websites. Are there any questions about that process? Do you see how the intersection of a set and a Z set, or the fact that Z sets are here and ordered, is a big part of what makes this work? It's the glue that holds all this together. Any questions? So when don't we want to use this? When is Redis a bad idea? If I have a lot of complex relationships between data sets, Redis does not allow us to define relationships concretely. I can do it on the application layer if I want to, but there's no concrete way for me to define that. If I have a lot of operations that are logically grouped together, you'll notice that a few operations that are grouped together are okay. In this instance, I have a vote that changes the score of an article and adds the user to a set. You could think of that as a tiny transaction, right? Transactions don't exist. I don't have transactions, but you could think of this as a group set of operations. If I have very large groups of operations, Redis is a dangerous choice to implement that, because there's no atomicity here. There's no rollback here, right? So if something happens halfway through that long list of grouped operations, I'm out of luck. For small groups, the odds of that happening are pretty low. But for larger groups, that's definitely a risk to run into. If I'm looking for specific data, Redis is tricky to use. For example, if I want to find, if I just want to go through one of these Z sets, right, and look for a specific value that occurs here, or if I want to go through a hash set and look for particular values that appear in my hash map, Redis does not really provide ways of doing that. I cannot target things by value. I cannot look things up by value. There's not an easy way to do that, other than just pulling all the keys, right? Which becomes very time consuming. SQL has a great way of doing that. It's called a where clause. So SQL databases are great. And then you see operation by sets here, which I've been touting as one of the nice things about it. But something to consider here is that this is basically to perform this intersection, what needs to happen? It's a nested for loop situation, perhaps, right? I have to check every one of these against every one of these to see if I found a match. So while Redis has the capability of doing that, you have to remember that Redis's ultimate goal is to be fast. And anytime I perform operations like that, I'm slowing things down, which could have negative effects. For simple stores and retrievals, that's where Redis really shines the most. If you are interested in this and you want more information about it, there are lots and lots more use cases online that you can find of people using Redis for various applications. It is very popular. It's very common. If you get into the web development space, you are almost certainly going to run into a key value store at some point in your career. It may not be Redis exactly, but that is certainly a popular one. I think that's only, yeah. Are there any questions about key value stores before we take a look at the next one, the graph database? All right, so we spent a lot of time talking about key value stores. We're going to talk about something totally different now. We're going to talk about graph databases. And the most popular graph database by far is called Neo4j. I don't know what the 4Js are. Perhaps they are, I don't know. Neo4j is developed by a Scandinavian company, so those J's could be anything. I don't know. But regardless, the graph database itself has a few major components. We've got nodes and edges, of course. It's a graph. We've got nodes and edges. Notice that the edges are directed. They have a direction associated with them. And then we also have properties. So nodes have properties. I can record information about each individual node. And then I also have tags. I can group nodes together. This node represents a book. This node represents a book. This node represents an author, right? So I can categorize my nodes. I can apply tags to them. So let's talk about why we might want to store our data in that format. On the right-hand side, this is meant to represent an example of a relational database. If I want to access data across multiple tables in a relational database, we use a join. And I have to go through and I have to exploit that relationship, typically a one-to-many relationship, right? So in other words, another way of thinking about it is that our relational database is prioritizing the data structure itself, the table. It's really prioritizing data contained within a table in rows and columns format. Any data that I can store in that simple format is going to be easily accessible. If I have to combine those, though, if I have to exploit relationships, that's a much more time-consuming process. So what the graph database is trying to do is say, well, what if we emphasize the relationships instead of the tables? What if the relationships are the emphasis, not the tables? So we're going to store things in nodes, which, there's no more entities anymore, right? Or if you do have entities, they're now spread out. I've got many nodes that are spread out over the entire graph. But I have a lot of relationships, a lot more direct relationships between my data that are very easy for me to traverse, as opposed to a join, which could even be that worst case scenario, that nested for loop, having to compare everything in one table against everything in the other table. Here, it's just as simple as following the edge, right? Take the edge, see where it goes. So we're really thinking about data structured around relationships as opposed to structured around tables. And so if you're trying to design and implement a graph database, what should you be looking for? What kinds of things should you be looking for? We want designs that will be easy to write queries for. I'm actually going to show you some queries here in a little bit. We want to have use cases that are aligned to the relationships and not the data. So think about what that means. Down here at the bottom of this slide, we have an example of relationships based on songs. So I see song right here in the middle, and I have artists and record companies and all that stuff, right? If I'm interested in performances, if I'm interested in exploiting this performance relationship, this could be a great example of when to use a graph database. If all I'm interested in is querying data directly related to the songs themselves, that's a much more data-centric, right? Table, row, column, tabular-centric way of thinking about my data. There's nothing wrong with making a song entity in a relational database and writing queries against that. So relational databases have their purpose if what I'm interested in is very data-centric and not relationship-centric. So really, I'm going to want to look for data that has many relationships. The example here is an n-area relationship. I don't want linear graphs. Graphs that look like a linked list are not good. I really want graphs with many branches, many relationships across many different nodes, so that we can try and exploit those relationships as much as possible. It can be very tempting to try and, see if I can zoom in on this a little bit more, sorry. It can be very tempting to try and store too much data in the nodes themselves. Again, the relationships are the star of the show here. So if it's possible for me to abstract some information out of a node and express it in the form of a relationship, that is an advantage in a graph database. Instead of listing alcohol percentage here as a property of the node, I can actually abstract that out. It says has alcohol percentage, and then have an alcohol percentage node. What that allows me to do is now more easily query across that particular property than it would be if it was embedded in the node directly. We can still do indexing. Indexing still exists. We just create nodes. Earlier I said, we want to avoid data that looks like a linked list. Well, actually, an index is typically implemented as a linked list, where every entry along the linked list is going to be connected to nodes that share that value. So here you see I'm indexing based on alcohol percentage. So all of the beer in this database that has an alcohol percent of 6.2 would be tied to this node. I can quickly and easily find what I'm looking for by traversing this list and getting off, right? Or it can even be more complex than that. Here is an index by date. Here's an index by date. If I want something for a particular year, right, I can go find the year node that I'm looking for and then all events that occurred down here at the bottom that are children of this node took place in that year. If I'm looking for a particular month or a particular day, it's the same story, right? Find the node of interest that I'm looking for. All children below that node took place at that particular time. So indexing can and actually should be used with your graph databases. Some things that you should try to avoid. A lot of these are kind of the opposite of things that we've already talked about, or similar to, I guess. Dumping too much stuff in the properties. We saw an example of this before. So instead of dumping too much information in the properties here, think of expressing this as a relationship instead. Speaking languages could be seen as a relationship as opposed to a property. That's going to lead to easier queries. Try not to cram. This is similar to some of the things we saw with relational databases. Try not to cram multiple entities in the same node. Try and have clearly defined nodes. So you've got things like language and currency all embedded in this node, when really we could abstract those out into their own nodes and express relationships. Almost any instance in where we can express more relationships is going to be advantageous for us in this database. This one's kind of obvious and also kind of funny to me. If you just have a big pile of nodes with no edges, is that even a graph? I mean, I guess technically it is. I don't know. I suppose technically it qualifies as a graph, but it's not going to be very easy for you to use. So here is kind of the opposite extreme. Many of the examples that I've been talking about before now have been saying, make more relationships, draw more edges. That's what the graph database wants. More relationships, more edges, more edges, more edges. Well, there's an extreme. If I have too many edges pointing at one node, it can be very time consuming to access that node since it's processing all of those relationships. So one thing that you can do to try and avoid this problem is to sort of make these little meta nodes to try and disperse the relationships out. Build in a couple of extra layers so that there's not so many nodes, so many edges going into one single node. So you can see here that Lady Gaga and Madonna have lots of fans. Instead of having all of the fans point directly to them, we've included some meta nodes to kind of spread those out a little bit, just to make it perhaps a little bit more efficient on the processing side. And then, yeah. So interestingly about graph databases, they provide consistency, and the way they provide consistency is in the form of transactions. Mongo doesn't really have transactions. Redis definitely didn't have transactions. Neo4j does have transactions. I can run transactions. That also implies, consistency implies that I can distribute my data. I can scale this database out by having it spread out across multiple servers. I can distribute it, which will then increase availability as well. So a lot of the things that we talked about with our SQL databases, Neo4j has also decided to implement as a matter of practicality. Let's take a look at how this actually works. I've got it installed on my computer. I've got some sample queries set up for us. So the query language is called Cypher. It looks kind of like SQL. There's some stuff that is kind of SQL-y a little bit, and then there's some other stuff that's very much not. So let me fire this up and I'll show you some examples. Do I need to log in? I don't want to log in. Go away. Okay. I have a database from earlier that I'm going to go ahead and start up. I thought I had this started, but apparently I closed it. Sorry about the delay. It's taking a long time. There we go. All right, and I'm going to pull up a browser, which is going to allow us to start typing in some queries here. So this database that I'm starting up has nothing in it right now. So the first thing that we're going to need to do in order to be able to run some queries and do some actual work is to create some nodes and some edges, right? So the way that we can do that using Cypher, I've got some examples in Notepad over here, is with create statements. So we're going to be talking about movies today. So create a node with where this is you can think of this as a variable name, right? This is a variable name for the node. It is a movie, that's the category. And then what are the properties that it has? The title is The Matrix, it was released in 1999, and there's the tagline. I'm gonna create some more nodes. Here's one for Keanu. He's a person. He's more than a person, really. Let's be honest. There's some information about him and all the other people. So I'm creating, I don't know, 8 or 10 nodes. So these all create nodes, and then I have to create edges between the nodes. So that's what these statements are down here. I'm saying I'm going to create an edge between Keanu and the Matrix that states that he acted in the Matrix, because he did. And then not only that, but my edges can have properties as well. So I'm including a property on my edge indicating that the role he played in the movie was Neo. And then I can, include other relationships here about these are the Wachowskis, right? Who directed the movie, and other actors, etc. So this will create, half a dozen nodes. I'm going to cheat though. I want a lot more nodes than that. So I'm going to cheat and load up a database that's already on here that has a lot more nodes than this that I don't want to type out because it would take too long for me to do that. I will just copy this. You can see it's 500 lines, right, worth of nodes to give us a database to play around with. So it's making us a graph, a movie-based graph for us to use. And here it is. It's got a nice little user interface on it that we can play around with. So it's centered me on Tom Hanks, which is fine. Can I zoom in on this? I don't know. So I see actually, I don't know what, there must have been another query at the end, sorry. There's more nodes than this. This graph should be bigger than this. But anyway, I'm currently looking at Tom Hanks. I can see all the movies that he's acted in, and some other information about people that have acted in movies with him and directed movies that he's been in, stuff like that. But what I'm really interested in is, all right, how do I use this graph to tell me some actual information? How do I pull some information out of this graph? So let's take a look at some different queries. We're going to start with some simple stuff and work our way up to some more complicated stuff. So if I just want to find Tom Hanks in my graph database, probably easier to see here actually. I'm going to use a match statement. That's Neo4j's equivalent of a select query, right? I'm going to use a match statement. Again, this is a variable name. This is then the criteria that I'm looking for. I'm looking for a node that has a property with the name of Tom Hanks. And then there's a return statement, which feels a little awkward. At least for me, this is awkward. It took me some getting used to write return statements at the end. But if you think about what's actually happening here, I've got a giant graph, and I'm querying some subset of this graph. So my return statement is defining what subset of the graph I actually want to see as my result set. So in this case, I'm just returning a single node, which is not the most exciting query in the world, but it will return a single node. It's taking a little while. My computer's running slow. So there we go. I have found a single node, right? And so that's pretty simple, but we can do more interesting and more complex stuff than that if we want to. Here's another one that would just return a single node, this time for a movie called Cloud Atlas. Let's take a look at something that does something a little bit different. here I'm saying find all of the nodes that are marked as people, and then go extract the names out. So find the names of people in my database, and just give me the first 10 that you can find. And what you'll notice, the result of this query looks like it's not actually going to be a graph. Since I told it to find the property directly, it looks like a table. It's like a table with rows and columns. So I can actually still get tabular data out of my graph, depending on the query that I structured. And just to make something that looks even more like SQL, here's a where clause. The syntax for this looks very similar to a where clause like you would expect in SQL. Property is greater than 1990 and less than 2000. So all movies that have been released in the 90s. None of these examples actually query across relationships, though. So what I think is especially interesting about this database and we're talking about is how do I write queries that move across relationships? So here's some examples of that. And you can see the syntax starts to get a little bit verbose, perhaps, one way to describe it. Locate the node that has a property called name of Tom Hanks. Follow any edges from that node. Follow any edges from that node that indicate that Tom Hanks has acted in something, right? The node is labeled as being an acted in. Anything that you find on the other side of that, I'm going to give a variable name and say those are movies, right, that Tom Hanks has acted in. And then return Tom Hanks and the movies that Tom Hanks has acted in. So this will actually be a graph this time. We have queried across a relationship. I want to see Tom Hanks as well as all the movies that he has acted in. I should get a nice little subgraph, very bouncy subgraph. Okay, there we go. Of Tom Hanks in all the movies. This is not a comprehensive list. I think Tom Hanks has probably been in more movies since then, but of the movies in the database, these are the ones that he's been in. We can get more complicated than that, though. I can follow more relationships in a single query if I want to. So if we take a look at some of these other queries, for example, this one. Find Tom Hanks and find the movies that he acted in, and then here's another relationship, right? So from those movies, see if there are any other relationships for other actors that also acted in that same movie. We're going to call those co-actors. And then I can return the names of all of the people who have been in a movie with Tom Hanks. Or if I wanted to see this in graph form, I could actually even see this in graph form as well, right? I could modify this. I could see it as a list of names, or I could even modify this query a little bit. Here's the list of names. If I actually wanted to see the graph, instead of returning coactors.name, I would return Tom, M, and coactors, and it will draw the relationships between those nodes. And now I have a much bigger graph than I had before. Hard to fit on the screen, but here's all the orange ones are the movies that Tom Hanks has acted in, and then I can see all the other people that were also in those movies, right? They were also in those movies. And so we could even use a database like this to answer that classic movie trivia question with the 6 degrees from Kevin Bacon, although I think it's only 4 degrees at this point, right? How many movies do I have to traverse to find a relationship between an actor and Kevin Bacon? Here we're saying start with Kevin Bacon, take any 4 edges that you can find, right? I don't care what the edges are, just 1 hop, 2 hops, 3 hops, 4 hops. Anything that you get to from 4 hops away, right? That's Kevin Bacon's circle, which should be everybody. That's the theory, right? Should be all of them. and then return all of the unique results that you have found. So we can post this in. And find all of the nodes that are 4 hops away from Kevin Bacon, which is, oh man, hello. Pushing this to the limit.
Where is?
Yeah, that was my question too. Where is Kevin Bacon? Oh, you saw him? Oh, he's right here. I see him. I got him. He's right here. So, a couple things to pay attention to here. One, clearly my computer is not the best for this purpose, but I think it's important to point out that while I can browse the data this way, in practice, if I'm going to be querying against a graph database, I don't need to see all the bouncy nodes going all over the place, right? Like that's fun, but it's not necessary, like most things in life. I know, it's sad, but we're getting to be grown-ups now, so watching things bounce across the screen becomes less important the older that you get, unfortunately. Sorry you had to hear it from me, but it's true. So, you know, a query could just return the list of names as one example. But all of the people on this screen, which I actually think this might be the entire database, or at least a very good portion of it. Is there a way that I can zoom? I don't want to rerun it. That would take too long. I'm pretty sure there's a way I can zoom, but I don't know how. I don't know what the hotkey is for it. Anyway, all of the nodes that you see on this screen right now are 4 hops away from Kevin Bacon. And that's cool and all, but what if I wanted to find a specific person, you know, and how many hops away is this person from some other person, right? Could I find that out? And the answer is yeah, absolutely, we could. So if I'm interested in seeing an exact relationship, right? How many hops are between Kevin Bacon and Meg Ryan? Well, there might be multiple paths. It's a graph. Cycles exist, right? It's a graph. So there are functions. Find the shortest path. Find the shortest path. You can put some of that 247, right, to good use here. Find the shortest path between this node and show me what that path is. Show me what the path is that you came up with. I have to be honest with you, my movie trivia knowledge is not great, so I don't know what this path is, but we're about to find out. Kevin Bacon was in Apollo 13 with Tom Hanks, who was in Joe versus the Volcano. I have not seen that movie with Meg Ryan. So there you go. That's 1, 2, 3. That's 4 hops. 4 hops away. 4 hops away. All right. Are there any questions? I'm trying to think if there's anything else that I had to show you. I don't think so. Are there any questions about this? It's a fun little tool to kind of get in and experiment and play around with. Let's talk about things from a more practical side for a second. What might you want to use this for? So it's not good for everything. There are certain situations where it works very well and certain situations where it doesn't. So if I have data that's got a lot of connections, think social network data, right? Think, or even computer network data, right? Those have very logical relationships, very logical connections that exist that would translate very nicely to a graph. It worked very well with a graph database. Things that are location-based work very well with graphs. So routing. I know one of the biggest use cases for these kinds of graph databases is it's almost a modern version of the traveling salesman problem, right? What's the shortest path for the UPS guy to hit all of these houses in a day, right? That's a problem that UPS cares about very much because they want to save gas and save time and get their packages out as fast as possible. So you could consider using graph databases for things like that. Recommendations. If I'm tracking the stuff that I've bought on Amazon and the stuff that you've bought on Amazon, and you see that there's a lot of overlap, like a lot of the nodes that I'm pointing to are similar to nodes that you're pointing to, well, then any nodes that maybe you're looking at that I haven't gotten yet might be things that I'm interested in, right? We've shown a lot of common interests. There's some stuff that's not common, but I might be interested in it if I knew about it. So maybe I'll make that recommendation to you. That's how Amazon works. That's how Amazon recommendations work. That's how Netflix recommendations work. Oh, you watched all 10 seasons of The Great British Baking Show, and so did this other person. Well, this other person really liked Downton Abbey. Maybe you will too. Actually, that's not true. That show sucks. Great British Baking Show is awesome, though. It's so heartwarming. I love it. Definitely check it out if you need to pick me up. Anyway, that's how that stuff works. There are use cases where this database would not be good, though, right? And I hope that's a important takeaway that you've gotten out of our discussion about NoSQL databases. They're not trying to replace SQL databases. That's not the goal here. The goal is to provide a database that's more flexible to your particular situation so that you can pick the right tool for the job at hand. And for a lot of jobs at hand, a relational database is the right tool, right? That is a fact. We're not trying to say that these are better or worse. They're just different tools. So, if you have things that are very data-centric, not going to emphasize the relationships as much, continue using your relational databases. They are good at that. They are good at those kinds of queries. They're good at those kinds of operations. If I'm going to be performing lots of aggregations and things like that, graph databases aren't very good at that. That's not something that they excel at. Believe it or not, graph databases actually excel at executing more complex queries. So if I don't have, if the queries that I'm running are relatively simple, it's probably better for me to just stick that data in a table and run simple queries on a relational database than to go through the hassle of trying to construct a graph database. Graph databases really want to do some more complex kinds of stuff. So think about that. Think about what you're trying to perform and the right tools for the job. Any questions? Any questions for me at all about this stuff? This is all free download, by the way. If you want to go out and download and install, you're more than welcome to play around with it. Lots of tutorials online. In fact, I should have plugged this at the beginning. I forgot. This book, Learning Neo4j, is fantastic. Fantastic resource for just starting out learning graph databases. And for Redis, did I include a citation here? Oh, I think it got cut off. I'm sorry. Got cut off on the bottom of the slide. The textbook that I used for Redis, if you're interested in a textbook resource for the Redis database, is a textbook called Redis in Action. So that would be a source that I would recommend if you're interested in picking up more information about that particular database. So I do have a practice problem. I unfortunately don't think we have enough time to do it. And also, too, I want to make it clear, I'm asking you to write some queries for the graph database. I want to make it clear right now before any of you go home and start getting super anxious about it. I'm not going to ask you to write graph database queries on the final exam. That's not something that I think is fair or reasonable to expect. Will I ask you questions about graph databases in general? What are they good for? What are they not good for? Yeah, that's fair game. Absolutely. Am I going to ask you to write graph queries? No, definitely not. But if you want some more fun and practice with the graph databases, here's a couple practice problems. I don't think we're going to have enough time to do that, but I'll go ahead and shut up. And if anybody's got any more questions or they want to chat with me after class, I'll stick around for the last few minutes. Question? You want to just come up and chat with me after? Yeah. And then otherwise, I'll see you on Monday. Have a great weekend, everybody. See you next week.